Great, thanks, and good day, everybody. Thank you for joining us here in today's webinar. Again, my name is Chris Munns. I am Senior Developer Advocate for Serverless here at AWS, and the title of today's webinar is Become a Serverless Black Belt. And what we'll be talking about here today are a number of tips and tricks and things that you want to think about when you are building serverless applications across kind of a wide spectrum of things. And so with that, let's get started. So again, my name is Chris Munns. I'm currently the lead developer advocate for Serverless. I've been here at Amazon Web Services for a little over 5.5 years now across a number of different roles. But background-wise, I am more of an operations person. I've done a lot of things in data centers. I've done a lot with the AWS Cloud before coming to work here at both startups and larger companies. And to me, this world of serverless, I find, is just so transformative, and it actually changes a lot of how we think about things. And so in my role today, I spend a lot of time talking to our customers, helping them understand what serverless might mean for them. And I think that this webinar today and what we're going to cover can really help bring to light so many of the topics around serverless that make it different, but yet familiar to what you might have been doing previously in the past. And so why are we here today? What is this concept of serverless? What does it mean for you to build a serverless application? Well, for us here at AWS, serverless really boils down to just a couple of things. And when we talk about products, that is. One is that there are no servers to provision or manage. This means no physical, no virtual, or even any containers that you would need to think about managing, scaling, provisioning, or potentially updating over time. Any of the products that fall into the realm of serverless for us here at AWS would automatically scale with usage, and you should never have to pay any sort of idle cost. And this actually is one of the key aspects of serverless, this idea of paying just for what you use when you're using it. And then lastly, availability and fault tolerance are built in. For those of you who maybe have been familiar with other AWS concepts, such as regions and availability zones, typically in the world of serverless applications, this isn't something that you do need to think much about. However, in this talk, we will talk a little bit about how you want to think about availability and making sure that your applications have the right level of availability for your need. But in general, these four tenets are kind of key to the space of serverless as we see it, and very much core to the products that we have. Now, in the center of this space is AWS Lambda. Now, Lambda is a compute service, as represented here in the center of this slide. And when we talk about a serverless application, again, typically Lambda is at the middle of it, and what we'll have is some sort of event source, and then some sort of service that Lambda maybe is talking to. And this could be a data store, it could be a database, it could be another service that's maybe exists over an API or some sort of other system call that you need to make. And in this case, the event sources that we have could be kind of aligned across a number of different things. We'll talk about some more of this here today, but they could be, for example, services that record a change in a data state, requests to endpoints such as API gateways, changes in resource state such as changes inside of the resources you have inside of your AWS infrastructure. And these can be used to create an event or a triggering call that initiates a Lambda function. Now, what is a Lambda function? At the end of the day, we maintain a large pool of compute capacity that executes code that you've written, which is your function. Today, we support 5 primary languages, so Node.js, Python, Java, C#, and recently Go was added just a couple of weeks ago. And inside of this Lambda function is whatever it is of the business logic that you have programmed. So again, whatever the backend you may or maybe don't need to call, it's completely up to you. And the application logic that exists inside of this is also completely up to you. And really what it comes down to, when we talk to our customers about what they love about serverless, it's about the ability to maximize elasticity, cost savings, and agility. Obviously, reducing the management burden and the overhead of having to deal with managing resources is one of the great benefits that exists. But it's these 3 key factors that we see really are what's so different about building serverless applications compared to really any other model that you have. So today's webinar, again, we're going to be talking about how you can make the best out of these 3 key factors. So in your serverless application, there are actually multiple points that you can optimize for. The first is our endpoint, essentially the thing that is going to get requested by, say, an application or a device or a person, in the case of an Amazon Alexa skill, which then might send a request to something such as a queue or another message service or even an orchestration service. We then have our Lambda functions. And then we have the backends that we might be talking to. And so across these, depending on the invocation path that you have and depending on the needs of your application, there's a couple of different points where we can actually optimize for elasticity and performance and for cost. And then how these services talk back into Lambda is also just as important. So we're going to go through primarily here today in regards to a serverless application, kind of three main aspects: the functions themselves, the invocations, and the interactions. Then we'll end up talking kind of across the board here how you think about serviceful operations for maintaining your serverless application. And what we're going to do today is basically take these four different things and organize them around the concept of optimization katas, essentially practices that you want to think of and be mindful and constantly be looking at other ways to improve what it is that you're doing. And so in this case, again, the four katas that we're going to look at is the lean function, eventful invocations, coordinated calls, and then lastly, serviceful operations. So for the goal for today is so that you could build a repeatable regimen for building highly resilient, high-performance serverless applications using all of the techniques and tips that we're going to talk through. So let's get started. The first kata, the lean function, really comes down to thinking about a couple of core concepts: concise logic, efficient or single-purpose code, and the ephemeral environment in which your Lambda function operates inside of. Now, let's actually talk a little bit more about what a Lambda function and the environment that Lambda provides for you is. So kind of at the center of it here, kind of the center of this bullseye, is your function, essentially your code and business logic that you have written to be executed based on your event. That function, or your function code, then runs inside of a language runtime, whether this be Java or Node.js or Go. Essentially, the language runtime provides core capabilities of that language, and it gives you the ability for you to write your application in that language. The language runtime then sits inside of an execution environment. Now, an execution environment you can think of almost as a small container, if you will, inside of a Linux operating system that allows your code to be executed based on your language runtime. And then all of this does sit on top of a compute substrate. So yes, there are servers behind serverless, but at the end of the day, they are, as you can see here, many levels below where it is that you interface with. Now, across this, there are a couple of key places where you have the ability to impact the performance, resiliency, scale, and cost impact of your serverless application. But then there is also a shared responsibility model of things that are on us at AWS to improve upon and keep iterating forward. Let's talk a little bit about the function lifecycle, what it is that happens when a function is actually executed. So I had mentioned before that AWS maintains a large pool of infrastructure that your functions run upon. So let's talk about what happens hypothetically if you had a brand new function that was going to be executed. What we have to do is take one of the resources inside this large pool of compute resources, align it with your account, and then we go and we download your code onto it. We start a new execution environment, or a container, if you will. We then have to bootstrap that environment. So let's say that you are running a Java-based Lambda function. You have to start up the JVM. And then we need to execute your code, what is actually inside the handler of your code, to respond back to the request that was just initiated. And again, this is what would happen the first time that a function was ever executed based on a request coming in from an event source. Now, what you see here, kind of below those top four parts that I mentioned here, are concepts such as full cold start, partial cold start, and warm start. In this case, what we're talking about is the state of the environment at this execution time. So when we start at completely zero, there's never been a request to a function before, we have to go through what is called a full cold start. This is where we have to completely give you a compute resource, start a new container, download your code into it, and then from there we can go and bootstrap your runtime, and then we can go and start your code. Now on the other side of this gray dividing line here, which we'll talk about here in a minute, the two aspects of a partial cold start and a warm start are things that would happen after we have already brought compute resources basically from our pool into a pool that we create for your account. And now in this case, we maybe don't need to start a new container for you, or maybe we need to start a new container on an already pooled compute resource. And so this does reduce the amount of startup time that you see in your application. Now, after that first invocation has occurred and we have what is now considered a warmed environment around, subsequent requests could land on this pre-warmed environment. So we call that a warm start. In this case, we don't need to identify a new compute resource. We don't need to start a new container. We don't necessarily even have to bootstrap a new runtime. We can just immediately execute your code. So across this, as you see, with the gray dividing line here in the middle, there are aspects of this which we, AWS and the Lambda team, have to optimize. And then there are aspects that you can optimize based on how you write your application. So let's talk a little bit about each of these. Now, I do want to say one thing about this, though, is that this is not a black box process to you. And in fact, if you enable AWS X-Ray on your Lambda functions, you can see this aspect of a cold start occurring during your Lambda invocations. So what we see here in this snapshot from AWS X-Ray, which is a profiling and tracing service, is we see the AWS Lambda service is actually getting a request. That is kind of the first arrow here on the left-hand side of the slide. The service then is going to actually go and create a new resource for us, or essentially initialize it. And then what we see here in the difference between the start of the AWS Lambda service and then the start of the AWS Lambda function is that cold start time. So we see here that for this function in its configuration, it took maybe just shy of about 2.5 seconds for it to actually give me the resource, configure it as it needed to be, and make it available to me. Then down below, in the very bottom line here, we see the initialization. You can think of this as the bootstrap for your environment. And then we have the execution of the function, which in this case took another roughly 5.5 seconds to completion. So all this is visible to you, and so you do have understanding of what it is and what is occurring inside of your function. So let's go back here again to our diagram and look at two places where you have the ability to impact the outcome, or effectively how long the cold start could take for you. Now you'll notice here that there are two arrows, one pointing to download your code, the other one pointing towards start your code. So let's talk about what your code can do in impacting both sides of the equation here. Having your Lambda function have concise function logic is one of the key things to understanding Lambda performance. Separating your Lambda handler, or essentially the entry point for invocations, from the core of the rest of your logic is one of the key best practices that we'll often recommend. In this case, if your function has any sort of business logic that it may take on that is independent or separate from others, maybe you get requests and you handle them different ways depending on the data that's received. Maybe you need to connect to different backends depending on that. By separating this out from the handler, you can actually streamline the amount of code and essentially work that the Lambda handler needs to do. So from a performance perspective, this is pretty key. You want to think about how your functions can be used to transform data, not transport data. A lot of the services that we have at AWS and a lot of the various services that can invoke a Lambda function can also directly take data from, say, A to B without having to go through a Lambda function. For example, Kinesis Firehose gives you the ability to take your data ingested from various methods through Kinesis, put it directly into, say, services like S3 or Redshift or databases. And so instead of having your Lambda function do that, allowing a higher level service like Kinesis Firehose makes a lot more sense. Another thing to think about is that you're essentially paying for any time that your function is doing I/O. So if you're reading a lot of data from a database or a data store, you're essentially paying for all of that time that you're transporting that data. And so you might want to think about different methodologies for reading only what you need. Today, across a number of the services that you would either have invoking Lambda or that Lambda would be talking to, you have the ability to essentially filter down the data that you're getting. So, for example, in the case of relational databases, making sure that you have strong indexes on those databases and that you're only performing queries to return data that you would need to use in your function. Using things like query filters in Aurora, or even using things like S3 Select, which was a feature that we announced back at AWS reInvent back at the end of 2017. I'll give you an example here of that last one. So we have publicly available on GitHub today a reference architecture for doing MapReduce inside of Lambda. And what you see here on the before side was the functionality for this reference architecture. And actually it worked pretty well. It ran relatively fast and executed the functions as required based on this example. And what we saw is that in the original sample here, it took 200 seconds, so it would have cost us roughly 11.2 cents based on us taking some of the data, splitting it down, and looking for certain key information inside of the data that was passed into the function. By implementing S3 select, what we're actually able to do, though, is greatly minimize this. So we see after using S3 select, we're now able to reduce down the amount of time to 95 seconds and the cost to 2.8 seconds. So just by making this small little change here in our code, there's a drastic difference in how our application both performs and how much it would cost for us to do this. So again, thinking about reducing the amount of data that you are transporting into your function and focusing on how you can transform that data is one of the key aspects when it comes to having a lean function. Another aspect to this is thinking about the efficiency of your code. So you want to avoid what we call fat or monolithic functions. These are essentially functions that perform or have too much capability inside of them versus the ability for you to potentially, say, split that function into multiple individual functions. You also want to think about controlling the dependencies in your functions deployment package. Today, it's very common to use open source packages that you could find from, say, NPM in the case of Node.js, or pip packages in the case of Python. And they provide a lot of value to you as a developer, but you can also run the risk of having too many of these dependencies doing very basic low-level things. And so thinking about where the trade-off is of using a package versus potentially writing some of your own code could be a big difference in terms of performance and essentially cost of your function. You also want to think about how you can optimize for your language. So for example, in Node, there are tools like Browserify or Minify. And pretty much across all the languages that we support today, there are various different tools that can help you reduce down unused code such that you don't have a very large deployment package. There's other ways that you could think about doing this. So for example, with our own SDKs, for many of them, we give you the ability to take selective subcomponents of the SDK. Now, the Java SDK rolls in at many tens of megabytes by default, just kind of out of the box. But you have the ability here, as we see in this snippet of a Maven configuration, to actually only include selective services. And this can greatly reduce the amount of code that we are putting into our deployable artifact, which again impacts the time that it takes to download that code. And so when we go back to the diagram in terms of the optimizations, this is one of the ones that you can do early on that can greatly help reduce cold start times. The smaller your deployable artifact, the quicker your functions will load. Now, going back to the shape of kind of your function or how it's organized, there's a couple of important things that you want to think about. One is that Lambda processes a single event per container, per execution environment. So the method of concurrency in Lambda is to have multiple Lambda functions be executed, not necessarily to pack a single Lambda function with parallelization. Previously, before we announced that Lambda supported up to 3 gigabytes of memory configuration, you only had a single CPU core. Now you have 2. So even doing things like multithreading was not necessarily a big performance booster, given that you only had a single core before. But again, you don't want to think too heavily about making use of multithreading inside of a Lambda function versus allowing there to be multiple invocations and multiple functions then executing at the same time. There's also no need for there to be non-blocking execution on the front end of your application. And so because of the way that Lambda functions work, you can split up your application logic such that you don't have Lambda functions that are sitting around waiting for other I/O or other work to happen. And then lastly, remember that containers are reused. So we talked about the cold start methodology, and then we talked about how after a first invocation in an environment has occurred, you have the environment itself stays warmed for a period of time. And so what you can do is actually make use of the fact that there are certain aspects of the bootstrapping of your function that only have to happen once, and then ideally never need to happen again during the life cycle of that execution environment. And so one thing that you can do is lazily load variables in the global scope. This can definitely help with streamlining the execution part of your function versus just the bootstrapping. Another thing is don't load it if you don't need it, right? So if you don't need packages, or you don't need libraries, or you don't need certain variables that are going to be used in every execution, think about only initializing those when they're absolutely needed. Now in Lambda, there's really only one knob that you can turn when it comes to thinking about the performance, or essentially how you provision a Lambda function. And that's the amount of memory that a function gets. And so today we support everything from 128 megabytes all the way up through 3 gigabytes of memory for your Lambda function. And again, as you turn up that dial for memory, you also get more CPU. So we proportionally increase the CPU as you increase the amount of memory. This also includes networking capability as well. And it's important to remember that while your function may not need all of the memory that you've configured it for, you might have a function that is much more CPU intensive in your business logic. So we see here an example of where this can play out. And what I've done here is actually color code across both the timing and the cost for a given example of a function. In this case, where we're calculating 1,000 times all the prime numbers that are less than a million. And we see this across 4 different memory configurations: 128 megabytes, 256 megabytes, 512, and then essentially a gig. What we see here is that the times and as well as the color, red is the worst, green is the best, yellow is the second best, and orange is the second worst. So what we see here is that while the 128 megabyte configuration did cost us the least, it also took the longest. Inversely, the 1 gigabyte configuration took us the least amount of time, but it actually cost us the second least. So, and it actually cost us very, very closely to what the 128 megabyte configuration would have cost us. So in this case, because this workload is so CPU intensive, by configuring it for a greater amount of memory, we can actually get a much greater performance without incurring a much higher cost. And so this is something that you'll want to think about when you think about what it is that your function is doing. Is it very CPU intensive? If so, you can get a lot of performance impact from turning the knob up on memory, even though you may not need all of that memory in your function. And actually, a really great blog post that was done back in the middle of 2017 by New Relic highlights this exact phenomenon that we see here. So in this case, a 50% increase in memory changed the 95th percentile of a test that they were doing from 3 seconds to 2.1 seconds. That's a pretty significant decrease in terms of the latency of a function executing based on turning up the memory. And so you could definitely experiment with this yourself and have your function execute and turn up the memory or turn down the memory and see where the sweet spot is. One of the other great things out there comes from our awesome developer community that we see. So Alex here, who has the GitHub repo AWS Lambda Power Tuning, allows you to have a function be executed against many different configurations and be able to see the outcome of it. And you can actually use this as part of a load testing or stress testing of your Lambda function to understand what is going to give you the best performance versus cost. And so again, depending on your Lambda function, what it's doing in terms of its business logic, the various memory configurations can be impactful. So definitely don't start just at 128 megabytes and assume that's the best for you because it's the cheapest. You might again find that the cheapest might involve a higher configuration. So I already kind of hinted at this, that now in the higher memory configurations, in this case configurations that are larger than 1.8 gigabytes, we now actually give you multiple cores. So less than 1.8, just a single CPU, higher than 1.8 gives you multi-core. And so some of your workloads may actually benefit from true multi-threading. Note that you'll want to look at your language that you're using for this, and if there are any need for any sort of third-party modules for this. For example, Python typically requires that you include certain modules in order for it to make use of multiple cores. And again, some workloads just aren't going to see benefits of this. If you have a workload where you take a message in from, say, Kinesis stream, and then you process it back out the other side, multiple cores are probably not going to benefit you too much. However, if you are taking multiple messages off of a Kinesis stream and processing them in parallel, multiple cores could help you. So IO-bound workloads will probably see gains, and however, those that aren't as IO-bound may not. So you'll want to think about this, as well as think about kind of the benefits of the higher memory configuration in terms of overall performance. Realistically, what this means is that at 1.8 gigabytes, you'll see the most amount of CPU performance that you could find in a single threaded application. And so that's really kind of the high point for where you would want to think about stopping in turning that knob higher, unless you needed more memory for your function itself. So another bit here to think about when we're talking about a lean function is removing orchestration in code. And essentially, if you have logic inside of your function that involves your function waiting for a response or doing some sort of sleep and then checking for data again, this is actually a very poor practice and one that we very much discourage with Lambda. And in fact, what you're much better at doing here is having a Lambda function that initiates a call or kicks off work on another service, and then having another one that comes and polls to see where this is. Again, you're typically not doing this as part of a synchronous request, but more often a asynchronous request. And so in the case of this, we recommend that you use something like step functions. In this case, what you can have is a step functions workflow that submits a job, and then another function that does a get job status, and then essentially can have the logic inside of step functions to understand things like back off and retry and failure. And reducing the orchestration code inside of your function also will help make your function much more concise in terms of the logic and the amount of code that exists inside of it, which will again help with overall performance. So kind of gone through a lot of things here in this first kata. Again, concise logic, efficient single-purpose code use, and then the ephemeral environment. There are things that you can do with this environment, but largely speaking, they kind of come and go as part of the platform. So the next thing we're talking about here is eventful invocations, succinct payloads, resilient routing, and concurrent execution. Now, going back to our diagram here from earlier, when we talk about invocation paths, we're talking about all of the different ways that a Lambda function could be interacted with. And some of these will actually overlap with each other in terms of how you could use them or in what ways you would want to potentially invoke a Lambda function. But you do really want to think about how each of these individually might best fit. So I like to use the term of gateways and routers. So one common misconception is that if you need a Lambda function to be executed by, say, an HTTP call or as part of another client that you own, that you must need an API gateway. This is not true. So Lambda functions actually have their own API for invocation. And if you control the client, let's say it's another service or it's a mobile application or it is an application even that's on-prem, you don't necessarily need an API gateway in front of your Lambda function. You can actually just rely on AWS's SDKs and using things such as IAM permissions and credentials to allow your Lambda function to be invoked. Now, if you don't have such control over the client, let's say you're building an API to be consumed by many different clients, or an API that needs to be consumed by, say, many different services that maybe you don't have direct ownership over, this is where you'd want to think about using an API gateway. So again, two different kind of models for performing essentially the same types of invocation. Another thing to think about is that back in 2017, we launched the capability in API gateway called regional endpoints. This is an endpoint that is not fronted by Cloud Run, but instead exists only inside of a region. So for service-to-service calls inside of a region, we see that regional endpoints are much faster in terms of not having the overhead of going up to a CloudFront point of presence. Another thing that you want to think about here is if you are using services such as S3 or SNS that give you the ability to provide prefixes or even filtering on tops of messages, then this could be really key to how you digest those messages. You might find that you have, say, an S3 bucket that gets lots of different types of content in it, but certain Lambda functions might only need to process certain events from there. So instead of doing that filtering logic inside of your code, make use of event prefixes. The same thing goes for SNS messages. Make use of the message filtering that's there. And again, what we're looking to do here is reduce the amount of requests going to our Lambda functions that may not be necessary, as well as, again, invoking them the right way depending on how it is that we need to invoke them. So this directly kind of aligns with my next point here, a concept which we call succinct invocations. So you really want to kind of look at the events that are coming in and understanding the importance of them. And again, this lends itself to thinking about what is the right invocation model for you. I could put a message into an SNS queue, I could put a message into a Kinesis stream. Those are, however, two very different services that provide different capabilities. So what is the provenance of this message or of this event, right? What happened for this notification to occur? What is going to be the thing that is going to invoke it? You would use an SNS topic very differently from a Kinesis stream. And when you think about the user interaction that would lend itself to eventually invoking a Lambda function, or I should say maybe the service interaction, this can help you decide which one is better. Again, an API gateway may not be the right thing if you know that you want to pass a message from one service to another. SNS might provide a better mechanism. Other things that you might want to think about is there some aspect to this payload that is important for the identifying of what it is that initiated the request? So API Gateway gives you the ability to send all sorts of request information, such as headers or potentially authentication or authorization information to the request, whereas you may not need that for the actual execution of your function. So how can you go and streamline down the amount of data that is in that invocation? Again, thinking about the service that you use to invocate and the use case. Another thing to keep on top of, depending on your use case, is that there are certain payload constraints. So for example, an async invocation can only handle 128K in the payload for the constraint. And so in that case, taking a large blob of data and putting it into an SNS topic is potentially not going to work out if it's going to be larger than that. In that case, you might want to think about using something like S3 as the invocation model for a Lambda function. And so you want to avoid large files on the inbound. You also want to think about large files on the outbound, depending on the service that you have set up, and depending on if you're talking about things like synchronous requests, there are certain limitations that might apply as well. And this brings us up to another point here. If you are going to use API Gateway, you don't just have to stick with JSON as essentially the wire protocol. API Gateway does support binary protocols, and so you can actually do things like use protocol buffers. So there was a really great, awesome blog post by a gentleman named Dian Cui, who happens to run a blog called The Burning Monk. And on it, you'll see that he provided an example of using protocol buffers with API Gateway. And what he found was for the same message to go over the wire, protocol buffers was essentially 40% smaller compared to the default JSON response that he would have transferred. And so this is important from a performance perspective in terms of speed, in terms of how much data you have to send, latency of that, as well as potentially the cost of processing the data back and forth on the wire. And so you can support binary protocols inside of API Gateway, and depending on how much control you have over the clients, this might be the right move for you. And then lastly here, you want to think about the resiliency of your events. So Kinesis and SNS, or SUS in this case, support very different types of messaging capabilities. Kinesis supports the ability for you to have order of operations, as well as resiliency of your Kinesis stream, such that you can go back in time and replay events up to a certain horizon or event point. SUS gives you massive amounts of concurrency, both in an unordered and ordered way, but it doesn't give you any sort of sequential control in, say, a multi-stream type of a setup. With SQS-based events, or in this case, ones that you would pull off in an asynchronous model, you do have the ability to potentially take those messages and if they have failed, potentially put them into a dead letter queue, whereas that's not something that's possible today with Kinesis. So different resiliency, different scale models, different durability models, these are all things that you want to think about based on the use case that you have. So in some places, Kinesis might make sense. In some places, SQS might make sense. But these are all going to be things that you need to think about. You also want to think about how Lambda scales from a concurrency perspective, not a transactions per second perspective. So for example, if we have a very simple invocation model where we have requests, say, coming in from an API gateway, those can all effectively in parallel cause Lambda functions to be invoked and execute and respond. So there's really not any sort of model that we need to think about in terms of a blocker and parallelization beyond the invocation model. For things that are queue-based, we might be thinking about, is this a FIFO queue? Is this an unordered queue? How often are we pulling the queue? And so that is going to impact and potentially act as a concurrency throttle based on the concerns that you might have there. And then for stream-based solutions, in this case DynamoDB streaming or Kinesis streams, effectively the number of shards that you have and the messages that are coming into those shards act as a concurrency model, and potentially as well as a concurrency throttling action in terms of how many Lambda invocations you're going to have at a given point in time. In the case of stream-based, you're typically talking about a single message off of a stream or a batch of messages off of a stream in a given sequential order. And so that nature could impact the overall scalability of your ability to digest information. And so in thinking about concurrency versus latency, there are various different trade-offs and aspects to think about. When we talk about things like streams, so for example, Kinesis streams and DynamoDB streams again, there's a maximum theoretical throughput that you have in terms of the number of shards times 2 megabits per second, or megabytes per second. The effective theoretical throughput is the number of shards times the batch size over the function duration times retries until expiry. So it's a little bit more complicated to think about what this actually is going to look like based on how your function is configured and based on your code logic and what you're doing here. So what you could find is if the put rate or the ingest rate is greater than your theoretical throughput, you could end up with a growing backlog of data, in which case the reaction to that is to add more shards. And this again really only factors in for streaming invocation models. For everything else, your maximum processing rate looks like the maximum concurrency that you have divided by the average duration of your functions based on basically the events per second. And then the effective processing rate looks pretty much the same. The effective concurrency over the average duration of the function execution gives you the events per second that you can consume. And so if you're talking to a backend system, these two things are very different in terms of thinking about how you think about limiting concurrency, as well as thinking potentially about how important durability is. If a Kinesis stream, or if a Lambda function feeding off of a Kinesis stream experiences a failure, I know that I have durability that is sequential in nature and that I can go back and do replays. If I'm getting messages, say, off of an API gateway, or off of an SNS topic, or off of, say, a queue, there are different things that I have to think about. So this is, again, one of the factors of how you build your application. Lastly, you want to understand how retry policies apply to this. So when we think about resiliency in applications, we definitely want to think about the durability of the messages. We want to think about the ability to replay those messages. And in the case of Lambda, there are various different retry policies that exist. So in synchronous invocations, there is no retry that is done by the service itself. This would rely on your client knowing that there had been a failure and doing a retry. In asynchronous services, such as SNS or S3 invocations, the invocation is retried at least 2 times, and then could potentially go to a dead letter queue. In streams are retried all the time, basically consistently until there is a success, or until that stream times out that data based on the time to live of it. So 3 different models here based on the 3 different models that Lambda has for execution. Now, I talked about how asynchronous allows you to have retries before you can go to a dead letter queue. This is another kind of key thing that we always recommend for people to do, which is to enable dead letter queue for asynchronous invocations. In this case, what you can do is those messages can go to SQS or to an SNS topic to be consumed by potentially another application, or for you to pull data back out of SQS and re-execute it. So this gives you an added level of durability on top of the services that are providing those asynchronous requests. Another thing to remember here is that retries count as invokes. And so if you have a service that has a maximum concurrency on, say, the backend, or if you have things such as concurrency limits placed upon Lambda functions, those retries do count as individual invokes. And so you do want to think about how this could impact potentially the overall burstability of your application. If you do experience failures, can your system deal with what are sometimes called thundering herd types of resolutions? Great. So we've talked about through Kata 2 here, our eventful invocations, so succinct payloads, resilient routing, and concurrent execution. Let's move on to our third kata, coordinated calls. So in coordinated calls, we're going to talk about decoupled via APIs, scale match downstream systems, and then lastly, how to think about securing your environment based on VPC. So one of the benefits that you have with services such as Lambda is kind of the way that it naturally lends itself towards building microservices-based environments. And what that means is that you have the ability to create APIs and have those APIs act as kind of multi-purpose constructs inside of your application for things like security, throttling, providing things like usage tiers, and so forth. And so what we see here is 3 different services: an ingestion service, a metadata service, and then a front-end service. Now let's say hypothetically that our metadata service is constrained based on, say, the back-end data store that could be used. What we have here in this architecture are actually 2 different APIs that we have: our ingestion API, and then we have our CRUD API, and then we have 2 different Lambda functions that exist inside of this, where we could make use of the ability to effectively throttle or control access through those endpoints into our Lambda functions into the backend services that are provided. And so what we can do is essentially use these APIs and these API gateways to provide, effectively, you could think of it as an SLA or a control mechanism that gives us an availability contract. And so this gives us, again, the ability to control the flow of data or requests that come through the system, throttle where necessary, potentially do retries where necessary, without having to have a ton of logic built further back into our application. Now, just a couple of months ago, back at reInvent at the end of November, beginning of December 2017, we launched the ability for you to set the concurrency reservation, as we call it, for a Lambda function. What this does is it basically acts as a reservation of capacity out of the total amount of capacity that an account has, which today is, by default, a 1,000 execution concurrency. Note that this is not per second. This is just 1,000 at any point in time. We measure this in the sub-second rate. So it provides you the ability to say that I want a Lambda function to have a maximum concurrency of 100. But again, that maximum concurrency also acts as kind of a reservation to say that I always want this function to have the ability to go up to 100. And then it gives you the ability to cap upside on the upside of that barrier. So if you have a downstream service such as a database or a data store or an external service that you can only call so many times over a given period of time, you can actually use concurrency controls to act as kind of a scale match throttle to those backend systems. There's some other capabilities here. For example, you can use this as a kill switch, so you can set concurrency down to 0 and essentially block any sort of execution of a Lambda function. You can also use this to simulate various bottlenecks inside of your application. But this is a really important capability inside of Lambda to allow you to prevent anything that looks like essentially a DDoS or starvation of backend resources based on the fact that Lambda supports such high levels of concurrency. And again, that default limit of 1,000 concurrent executions at any point in time is just a default limit. It's very easy for you to go and increase that. And we have customers doing many tens of thousands of concurrent invocations. So the last topic we'll talk about here is VPC. I find that this is one that is quite often misunderstood here in the world of serverless applications. So let's talk through a couple of points or a couple things you want to think about when it comes to if you should or shouldn't use a VPC. So the question you want to ask yourself is, should your Lambda function be inside of a VPC? The first question is, does your function need access to any specific resources in a VPC? So is it talking to an RDS database? Is it talking to an Elasticsearch instance? Is it talking to another service that you own that is inside of a VPC? If not, don't put your function inside of a VPC. There's actually 0 added benefit to Lambda from a security standpoint to put your functions inside of a VPC. Lambda functions do not today, in execution environments that they run in, have any sort of external interface to them. They can't be reached over the network directly. They can only be invoked via API. And so from a network security perspective, the VPC gives you little to no added benefit. But let's say that you answer yes to this question. Do you also then, or does this function then also need to access resources in the public internet? If not, put the function in a private subnet and based on your network ACLs and the security groups that you configure that function for, it will be able to access the resources privately inside your VPC or over a VPN or direct connect link. However, if they do need to access resources inside of a public or on the public internet, then your Lambda functions need to have the ability to route via a NAT gateway. So they will have to have a NAT gateway. There are a number of different protocols that your Lambda functions will need to talk out of via, say, DNS and HTTP or HTTPS potentially. And so using a NAT gateway is basically the most scalable and efficient way for being able to support this. Again, if your Lambda functions do not need to access anything inside of your VPC, there is no reason to turn on VPC for your function. So why does this matter? Well, it turns out that running a Lambda function inside of a VPC actually does impact the cold starts of that function. So we see here the diagram that we showed earlier, and what we've expanded here in the middle on the AWS optimization side of things is the create VPC ENI and then attach VPC ENI. Now, these are two calls that are made to the VPC substrate that create a network interface and then attach it to the execution environment for your Lambda function. And it just turns out that the way that this call exists as an API takes a little longer than most. And so you do want to be cautious about, again, the need for you to have Lambda functions inside of a VPC. So basic kind of tips and guidance around having functions inside of a VPC. First, always configure a minimum of 2 availability zones. Now, typically for serverless applications, we talk about HA being built in. But as soon as you launch a Lambda function inside of a subnet, you're effectively providing a blocker or a box around how far it can scale and how it scales. So always think about having subnets across multiple availability zones for your serverless application. Another thought is give your Lambda functions their own subnets. Now, Lambda functions and the execution environments that they run on are going to consume IP addresses via the ENIs that are created. And so you don't want to think about there being any sort of resource contention between other services. You also want to give these subnets a fairly large IP range. Depending on the concurrency of your Lambda functions, you could end up consuming quite a lot of IPs. And again, you want to think about these as somewhat finite resources, in this case based on the scale of those subnets. And then again, just want to make sure this is very clear. If your functions need to talk to a resource on the internet, you need to use a NAT gateway. Great, so that's the third kata down, coordinated calls. So again, decoupled via APIs, scale match downstream via concurrency throttles, and then thinking about the need or not for you to run your functions inside of a VPC. Let's round out here now with our fourth kata, serviceful operations, talking about automated operations, monitored applications, and an innovation mindset when building with Lambda. And then at the end of the day, this is really about the tools that you can provide the people inside of your organization and how those tools can help them to greater make use of serverless, be more efficient in this space. So the first thing to start with that I'll often tell people is that there is a wonderful number of third-party frameworks that are just really awesome and can help you get started very quickly. I have here just an example of some of the more popular ones that we see. Apex, AWS Chalice, ClaudiaJS, the Serverless Framework, Sparta, Zappa. There's a number of these, but these are some of the ones that we see more often. Some examples here. So if I take ClaudiaJS and I want to build an API, it is essentially about 5 lines of code that I need to run, and then a single command. And what this will do is take a Lambda function with this code, create an API gateway, and then put together all of the various pieces of glue, such as IAM, roles, and policies, to allow API gateway to invoke this Lambda function for me, for my API. Similarly, in AWS Chalice, which is a Python-based framework, we can do the same thing. So again, about 5 lines of code, a single command, and it's going to go and create for me all of the resources that I need. If we expand upon this a little further, what a lot of these frameworks allow you to do is write essentially minified or simplified code that then expands into much more complicated code based on the framework libraries itself. So we see here that I have some very basic construct around application routes, some very basic constructs around error handling with API gateway, and various different types of HTTP method support, where if I was going to write this all myself from scratch, it would potentially be many, many, many more lines of code. But this is a very simplified example here. Now, if you don't want to use any of the third-party frameworks, and they all do have a certain level of opinionatedness and certain things that they're better at than others, we here at AWS also do provide kind of what I think is a much more straightforward, unopinionated tool for launching and managing your AWS resources. So in this case, we have SAM. So this here is our wonderful squirrel mascot, SAM. So in AWS serverless application models, or as we now call SAM, this is a CloudFormation extension optimized for serverless. So what this means is that we have a couple of new resource types that greatly simplify the work for building and launching serverless applications. In this case, we have functions, APIs, and tables. And now this is built directly into CloudFormation, so it does support the underlying capabilities of CloudFormation, such as parameters and metadata, outputs, imports, exports, all that kind of good stuff. You can find out more about SAM here in our GitHub link, github.com/AWS Labs/serverless application model. And again, all of these tools, both the third-party frameworks and SAM, exist to help make it easier for you to build and launch serverless applications. But when it comes to actually deploying and thinking about your deployment lifecycle, one of the things that we recommend is making sure that you have a strong delivery pipeline. Now, this is another place where you can lean on many different third-party tools, both open source or hosted or managed or enterprise versions that exist. In this case, this is an example of a code pipeline that can be used for deploying a serverless application. In this case, this pipeline has 5 stages: a source stage, a build stage, a testing, staging, and production environment. And it uses tools like code build to build my code, code commit to store my code. It makes use of CloudFormation for deploying SAM templates, uses Lambda for doing things such as running stub tests against my function, makes use of third-party API tools such as RunScope, provides a manual review, potentially by a QA team. And so thinking about your pipeline and how you could automate your serverless delivery is another really key thing to be mindful of. Now, when it comes to thinking about metrics and monitoring, there are also a number of things that are key to serverless applications. Now, built into almost all the products that AWS has is some level of either logging or metrics collection by CloudWatch. And products such as Lambda and API Gateway are no different. So in Lambda today, we capture 7 different metrics, but you also, inside of your code, have the ability to call the put metric data CloudWatch command to actually create custom metrics yourself. API Gateway has 7 built-in metrics for APIs today. For CloudWatch logs, in Lambda logging, basically anything that you output from your function gets captured by the underlying execution environment and then sent up to CloudWatch logs centrally. Same thing exists for API Gateway logs. You have the ability to capture a number of different kind of levels of logging, as well as specify custom formats for exporting. And so there's all sorts of great things that you can get out of API Gateway logs. And then lastly, CloudWatch Logs supports this concept of a log pivot. Essentially what this means is you have the ability to apply a regex against a line message, say pull out a certain data point, and take that data point and convert it into a metric that could then be alarmed against or just tracked in a dashboard. So lots of different capabilities built into here, as well as kind of various bits of flexibility as well. So what this means is that it can be very easy for you to automate the creation of dashboards, as well as have dashboards just in general, even if you had to make them by hand. We see here a very basic example of a dashboard for a single Lambda function and a single API gateway, where I've got kind of all of the pertinent information, very easy for me to find, and including things like alarms. Another tool that you have at your disposal is AWS X-Ray. So X-Ray is a profiling and tracing tool. What X-Ray does is it allows you to capture things such as HTTP or HTTPS calls, database calls. Basically, actually, you can pretty much make it capture almost anything that you want it to about your function, and be able to report back information such as the time that it took for it, so effectively the latency of calls, if those calls were successful or not, things like transactions per second, and so forth. And then from there, then be able to visualize that. Now we see here an example of how you can go about tooling this into your application code. And so at the most basic level, enabling X-Ray inside of your code is about 2 lines in the case of a Node.js example. We see here this top line, which is requiring the X-Ray SDK core. And then we see the second line, which is then wrapping around the AWS SDK. From here, any of the calls that we make using the SDK will be captured by X-Ray. So in this case, this function is putting data into an S3 bucket. And what I would get from this in my X-Ray trace is a map that looks very much just like this. And so I can see here the average number of requests, how long they took. The circle here being green means that so far all of my requests have been successful. If there have been issues or failures, there would be other colors in the circle there. I also have the ability here to see essentially a waterfall view. Now this is very similar to an image that I showed earlier in the presentation on understanding cold start times, but we see here an example of time that was spent by the service and then by the function and the calls that it made to S3. So lastly, what I wanted to mention here is that serverless applications open you up to quite a lot of different types of architectures. And you can think about how to evolve them over time, based on kind of everything that we've talked about here today. Now, while we don't recommend that you build things like serverless monoliths, they are kind of really the best way to start out. So starting with a single API-based service that has many Lambda functions behind it, all potentially talking to the same database, while you could potentially run into scaling patterns, for many people they won't. And so this is a perfectly fine architectural pattern to start with. Eventually what you might find is that you have to do something more like on the right side of this slide here, where you decompose your services into separate layers, into separate data stores, and maybe provide APIs that look at that data from various different angles. So don't be afraid to think that you can't innovate and incrementally change your infrastructure over time. Lambda is still meant to be a very flexible compute service, and so as you build and grow and expand your applications, you will definitely find that your architectures will grow as well. And then lastly, be creative. So we see people building all sorts of interesting tools inside of their organizations as serverless applications. And so you might find that there are things that make sense just to be built as little small Lambdas. We see here some examples from public blog posts of people building things that are both on the operational side, as well as things that exist as potentially customer-facing serverless applications. And so there's all sorts of different places, again, where you can expand into this based on the kind of wide range of technologies that AWS has to invoke Lambda, as well as the various different use cases that you could think of yourself. And so with that, we've covered our fourth kata here, serviceful operations. So again, automated operations, monitoring your applications, and having an innovation mindset, especially thinking about all the various different ways that you could use serverless applications and AWS Lambda to solve your problems. So with this, we've talked about 4 different katas today. Again, katas being basically areas of focus for you to iterate on and build up better practices and better patterns inside of your business. We have the lean function, so thinking about functions being concise, efficient, and ephemeral. We have eventful invocations, thinking about the succinctness of our code, the resiliency that exists in our invocations, and the concurrency that can exist of them. We have coordinated calls, decoupled, scale matched, and secured. Again, thinking about whether you do or do not need things such as VPC. And then lastly, serviceful operations. So how we can automate, monitor, and then make use of innovation inside of our organization to best use the capabilities of serverless. Everything that I talked about here today, plus much more, can be found on our homepage for serverless at aws.amazon.com/serverless. Nothing that I covered here today is anything that is secret or only available under NDA. This is all generally available information that you could find in our documentation, in our getting started, in our how-tos, as well as here there are links to things such as case studies, partner resources, getting started guides, and tutorials. So definitely encourage you to check that out if you're looking to learn a little bit more about this space. Again, my name is Chris Munz. I'm a senior developer advocate for serverless here in AWS. You could find me at munz@amazon.com or at Chris Munz on Twitter. Would love you to please provide information in the poll here at the end of this presentation. But if you've got further questions or you need some help, feel free to ping me, and I'm always happy to try and get you whatever help you might need. With that, we're going to open it up to some questions here. And again, want to thank you for joining us here today, and I hope that you join us at another webinar soon.